Hello my dear students, welcome to Learning Chemistry is Easy and Fun. Lesson 5, Coordination Compounds. Our topic this time is valence bond theory. At the beginning of the lesson we had discussed Werner's theory to explain the existence of coordination compounds, right? And it talked about primary valency, secondary valency, but if you noticed, it did not mention anything about the geometry, about the shape of the coordination compound, right? It never mentioned anything about the color of the coordination compound, what color a coordination compound will have and why, right? So, in order to overcome the drawbacks of Werner's theory, which was a very basic theory, we have propounded the valence bond theory, right? Now, this particular theory you have already done under the heading chemical bonding. We are just going to adapt it to coordination compounds. Now, valence bond theory says that the electrons in the valence shell, they will participate in bond formation, and we also explained hybridization, right? And when does this hybridization happen? When one atom approaches the other, there is a redistribution of energy within this second atom which is being approached. So I have atom A, I have atom B. B comes closer to A, wants to make friends with it, right? So there is a reorientation of energy within A, which is called as hybridization. And that is what we are going to talk about. The first point in valence bond theory says the ligand approaches the central atom and the central atom will provide a vacant orbital in order to accommodate the electron pair being provided by the ligand. Now, this situation is very much similar to, let us suppose, a guest coming to your house. So, what do? You make some space. So if some guest is coming to stay at your place, what do? You make some space available for the guest in order to make that guest feel comfortable, right? So the same thing, the central atom provides vacant orbitals into which the ligand can lodge the electron pair that it is going to donate or form a coordinate bond with, right? Now, in preparation for this, in preparation for the guest who's coming to your house, what do? You change some position of the furniture, you make some space in the cupboard so that your own comfort is not disturbed and at the same time the guest also is not unhappy, right? So you are all at par. Hybridization is something similar. Here, intermixing of atomic orbitals of similar energy takes place in order to form new orbitals. Now, these new orbitals are what we call as hybrid orbitals. Just like the hybrid variety of wheat, the hybrid variety of various fruits. What is hybrid variety? You take good qualities of one fruit, you take the good qualities of the other, and you have a new variety or new species, what we call as the hybrid variety. Now these hybrid orbitals will now have equivalent energy. Don't worry, I'm going to discuss more of this, but for those who already have a concept of hybridization in place, then this will be very easy. Number of hybrid orbitals is always equal to the total number of atomic orbitals participating in hybridization. I will be coming to that as well. And this is also equal to the coordination number of that central atom. If any of these words like ligand, central atom, coordination number are not familiar to you, please go to lesson 1 in this series, and all these concepts will become very, very clear. The hybridized orbitals arrange themselves so that they are maximum distance apart from each other and there is minimum repulsion. Otherwise, what is going to happen? Now, this is atom A and lot of ligands have come here, right? Now, this atom A will try to keep all the ligands happy and try to keep them away as much as possible so that it can accommodate them around itself, but at the same time they don't fight with each other. So there is minimum repulsion between them, and that explains why coordination compounds have regular definite geometry. Right? An interesting point over here, if you've already studied about ligands, about hybridization, is you do the lone pair, bond pair repulsion, lone pair repulsion, right? Now, all those form of repulsions do not come into play in the case of coordination compounds. That is why I said that we are going to adapt the valence bond theory that we have studied for atoms in order to explain the behavior of coordination compounds. You have to remember here that these are theories which were propounded in order to explain the behavior of substances, of compounds which are already existing. Okay? That is where chemistry is different from physics. Coming to the fourth point, ligand and metal. Now, if you see, I put 2 arrows. Forget about the down arrow. The ligand gives electron pair to the metal by coordinate bond, and this is what we call as the sigma bond according to VBT. That's the short form I'm going to use for valence bond theory. So, according to valence bond theory, the ligand gives a pair of electrons to the metal by sigma bond formation. Sometimes, not always, the ligand may have vacant orbitals into which the metal can give its electron pair in return. So it's like the ligand gets a gift for the metal in turn gives a return gift to the ligand. Right? This makes sense? But we name them differently. The gift is ligand to the metal, but the metal to the ligand is the return gift, right? So this is sigma bond and the return gift is called pi bond. Usually metals which have low oxidation state will have a tendency to show this bond formation, but a very important point that I had mentioned in lesson 1 also, we never count pi bonds towards coordination number. Please remember this. It is always the electron pair being given by the ligand to the metal which is counted as one coordinate bond. Right? Now, what is the next step that we are going to do? Point number 5. But before I rub all this out from the board, wouldn't it be better if you wrote this down in your own handwriting? Yes, the pen and paper chemistry. Please get a pen and paper or your notebook wherever you've done the earlier 4 lessons. Please write down these points so that they become your notes for ready reference when you are offline or when you are preparing for your examinations. I have tried to write as many keywords as possible. I would still advise you to refer to your curriculum book in order to write any of the points which I may have missed. I'm trying to simplify the concept for you, right? So get going. Copy these points and then we go on to point number 5. Point number 5. What are the various types of hybridization that could be undergone by the central atom in order to accommodate the ligand? It could be anything. sp, sp2, sp3, sp3d, sp2d, sp3d2 and so on and so forth. But you notice I put sp3d2 and here I put d2sp3. I put sp2d and I put dsp2. What's the difference? Aren't they the same? No, they're not the same. We are going to discuss them with the help of examples. So relax. It's very easy topic. Stay chill. Go step by step and I promise you'll be very happy with the lesson at the end of it. Sixth point. The non-bonded orbitals. That means those orbitals or those electrons which are present in the orbitals which are not participating in bond formation, they follow Hund's rule of maximum multiplicity. What is Hund's rule? It says that orbitals will first be singly filled and then pairing will begin. For example, you have the d orbital and let us suppose 7 electrons need to be accommodated in the d orbital. Now, according to Hund's rule, you will put 1, 2, 3, 4, 5, right? 6 and then 7. So, what you have done is, so if let's suppose you have 7 apples and you need to distribute them amongst 5 children. So what do first is to give one apple first to each of them and then again start going back to the first child, give him 1, to the second child, give him 1 and the other 3 children get only 1 apple, they don't get a pair, right? These we will see they can participate in what changes will take place. We will see when we discuss hybridization. Now this pair of electron for sure is not taking part in bond formation in coordination compounds and we call them as the non-bonding or the lone pair, right? Now coming to magnetic behavior, right? What is magnetic behavior? 2 types are shown by the coordination compounds. Either they are attracted to magnetic fields or they are repelled in magnetic fields. If they are attracted to magnetic fields, we call such an atom or compound as paramagnetic. And paramagnetism is always attributed to the presence of unpaired electron, whether it be an atom or a compound. Diamagnetic, on the other hand, are repelled in a magnetic field because there are no unpaired electrons to interact with the external magnetic field. So, paramagnetic situation will be something like this. Diamagnetic situation on the other hand would be something like this. So let's suppose I am talking about a situation where in my final compound I have this configuration. So because there are unpaired electrons, this particular configuration will cause the compound or the atom to be paramagnetic. On the other hand, if all these electrons are paired up, then it will be diamagnetic, that is repelled in an external magnetic field. How do we know whether it is paramagnetic or diamagnetic? This is done by what we call as the magnetic susceptibility measurements. Oh, such a big word. Don't worry. Break it down. Magnetic susceptibility. How susceptible, how prone, how easy it is for you to be affected. Magnetic susceptibility measurements means the ability of the compound or the atom to be magnetized in the magnetic field applied to a sample. That's all. That's all you need to understand at this level. We are not doing the technical definition. Magnetic susceptibility is ability to be magnetized. The extent to which the compound can be magnetized in a given magnetic field is magnetic susceptibility measurements. So, we've done the major points of valence bond theory. All this will not make sense unless we do examples. So, let's note down these points and jump to examples explaining the various types of hybridization and helping you to understand how the valence bond theory makes understanding coordination, or how the valence bond theory actually tries to make the behavior of coordination compounds a little more understandable, right? 5, 6, 7, 3 more points to write down. Let me start by taking a very simple example. You've heard of the compound diamine silver chloride, right? I'm just going to take the complex ion part. Now silver, atomic number 47. Write it in terms of the inert gas. The nearest inert gas is tryptin. So we have tryptin 4D10 5S1. It is showing an oxidation state of +1. That means one electron is done away with. That is why it comes into the oxidation state Ag positive. Therefore, the configuration of Ag positive now becomes square brackets tryptin. That means we end at 4p6. This is simple way of remembering how to go about it, and then 4d10. By the way, if you are not confident about writing the electronic configuration in terms of inert gas, there is a separate video on periodic table and periodic properties. You may visit that. So now when we write Ag positive electronic configuration 4d10, according to the Hund's rule, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? We've got 10 electrons in place. Now, ammonia says I have lone pair of electrons and we are 2 of us and we need to give our lone pair. Where will you accommodate? If it accommodates one lone pair in the 5s and one lone pair in the 5p, what will happen is the energy of one bond will be different from the other. So energy of this bond between silver and ammonia and the energy of this bond between silver and ammonia will be different. Why? Because here we are talking about the s orbital, whereas here the overlapping is with the p orbital. But experimentally it has been observed that the energy of both the bonds is the same. So the situation is the same. There is a guest who's come to the house. We need to do a reorientation. So before ammonia approaches, or let us say when ammonia approaches S and P orbitals, they say, okay, let us come together. We have to accommodate 2 ammonia ligands. So they come together and they make one single unit, but again made up of 2 compartments. So the situation becomes something like this. The 5p, the remaining 5p are here, whereas one orbital of S and one orbital of P have come together to form a single unit. But how many rooms will be there in that unit? Again, one from here, 2. The number of rooms in the house still remains the same, but we name them differently. Their energy will be the same. They will have equivalent energy now, and this we call as the sp hybrid orbitals, right? So generally we don't show it like this. What do we show it as? By means of these brackets or boxes, in order to indicate that S one S and one P. Now this one S means this one box from S and one from P. I'm not talking about 5s is the energy level, right? So one orbital from one orbital or one sub-level, it is the same, and one from P have come together to form sp hybrid orbitals. Now these hybrid orbitals have to be arranged so that they stay maximum distance apart from each other. There is no jealousy amongst them. They need to be kept apart. And how is it possible? What is this shape? Perfect. It's a linear shape where silver will be in the middle and ammonia kept away from each other. So what do we have over here? What will be the geometry of this particular molecule? We will have silver and we will have ammonia, and we will have ammonia. Bond angle will be 180 degrees. The shape will be linear. Hybridization will be sp. Coordination number is 2 because each ammonia is giving one pair or one lone pair of electrons, right? Will it be paramagnetic or diamagnetic? Yes, there are no unpaired electrons, so it will be diamagnetic, right? And this goes well with the experimental observations regarding this compound. So valence bond theory is, yes, apt for this particular example. Let's go on to example number 2. But before I rub this out, please copy it so that you are able to do a bit of example to yourself also, right? So this is sp hybridization, correct? If I have one of S and two of P getting involved, what type of hybridization will that be? Perfect. It will be sp2. How will you align the atoms now or the ligands now so that they are maximum distance apart from each other? Very good. It will be trigonal planar. That means they are being arranged in a triangular manner in one plane, right? So this will be my central atom, one ligand, second ligand, third ligand. sp2 hybridization. But we can't predict the paramagnetic or the diamagnetic behavior unless we see the electronic configuration of the central atom involved, right? Please make a note of this and we go on to example number 2. Now we are taking a compound of nickel. Can you give me its name? If you revise the topic on nomenclature, yes, it's tetrachlorido-nickelate 2, indicating that its coordination number is 4, oxidation number is 2. We are talking about nickel, right? What Werner had called as the primary valency and the secondary valency, right? Now nickel 28 is its atomic number. Electronic configuration in terms of inert gas, argon 4s2 3d8, correct? When it turns into nickel ion, it loses these 2 electrons from the 4s orbital. Now we could have a possibility here wherein 1, 2, 3, 4. So 1, 2, 3 and 4 pairs. That is, they pair up and we have 4s and then we have 4p over here, and we need to accommodate 4 ligands, means we could have 1, 2, 3, 4. These 4 coming together to form hybrid orbitals, in which case we would call it as DsP2 hybridization, right? But that means it does not leave us with any unpaired electrons. No unpaired electrons means it should be diamagnetic, right? But what we observe is experimentally this compound is found to be paramagnetic. In other words, this assumption is not appropriate. So what is the second option that we have? We have to accommodate 4 ligands. So the second option, let us show it maybe with a different color so that it's easier. So we have 1, 2, 3, 4. So we leave these unpaired electrons untouched. 1, 2, 3 are pairs, 4th and 5th are lonely. They are singly occupying the d orbital. And then we have 4s and 4p. Now because we have to accommodate 4 ligands, we need 4 vacant orbitals. So 1, 2, 3, 4, and they are all of the same energy. So we have hybridization over here. What hybridization would it be? Perfect. This would be called as, because you are involving 1 of S and 3 of P, we call it as sp3 hybridization. Now those who already have the concept of hybridization in place, what is the geometry of a sp3 hybridized atom? Tell me. Yes, it is tetrahedral. So we have the central atom here, right? Okay, this is my central atom. 1, 2, 3, and the 4th one. Again, we are trying to keep maximum distance from each other so that there is no jealousy, there is no war, there is no repulsion between them. Each of these bond angles comes to 109 degrees 28 minutes. I've shown it by different colors so that it becomes easier. You would have 4 pencils handy on your table. You can just hold it and get an idea about what we mean by the tetrahedral structure. And this tetrahedral mean, so we have here, we have 1. So let me denote the central atom by a big circle. And we have 2, and we have the 3rd one indicating that it is coming out of the board towards you, and there's 1 inside away from you, and the bond angle 109 degrees 28 minutes. It is perfectly in confirmation to the experimental observation where it is found to be tetrahedral, right? And because there are unpaired electrons, it is paramagnetic as well. So you need to understand over here that the valence bond theory is just trying to explain what is already being observed. It's not trying to dictate that, okay, it should be like this. No, it is that, okay, I have observed this thing. This could be its possible explanation, right? So this is not the case. We have NiCl4 2-. Because we observe that it is paramagnetic and it is tetrahedral, we explain it by saying that it has sp3 hybridization, which explains its tetrahedral structure. It has unpaired electrons, which explains its paramagnetic behavior. Have you noted this down? Should we go on to the next example? Are you able to understand? If not, just pause. Take a deep breath, relax, go through the points again, and then and join me for example number 3. There is no need to rush. Don't pressurize yourself too much and don't get worried if you are not able to understand in one go. I'm taking another compound of nickel only. Nickel bonded to CN group, right? Again naming it tetra cyanido. Yes, it's not cyano because it comes from cyanide, so it's cyanido nickelate 2, indicating that its coordination number is 4, oxidation state of nickel is +2. Experimentally observed, this compound is diamagnetic, right? Diamagnetic means it should not have any unpaired electrons, correct? All electrons should be paired up. So let's start with the electronic configuration of nickel. Argon 4s2 3d8 or 3d8 4s2, as you may choose to write. Ni2 positive, that means nickel oxidation state 2 positive, so it loses these 2 electrons from the valence shell. Now after it has lost these 2 electrons, diamagnetic. If I ignore these 2 unpaired electrons, it will not justify its diamagnetic behavior. So we need to pair them up. So what happens over here is when the ligands approach nickel, not otherwise, when approached by the ligands, the electrons, the lonely electrons in the d orbital, last 2, they pair up, right? Now all electrons are paired up. And I have the 4s and the 4p vacant over here, right? I have to accommodate how many ligands now? 4 ligands. So 1, 2, 3, 4, right? We need to have 4 rooms ready for the guests. So 1, 2, 3, 4 come together. There is 1 of D, 1 of S and 2 of P participating in hybridization. Hence, the name of the hybridized orbitals will be dsp2 hybrid orbitals. Right? How many of these will be there? 1, 2, 3 and 4. So total 4 dsp2 hybrid orbitals. Now dsp2 hybridization means the shape is not tetrahedral. Why is it not tetrahedral? Because we are involving d orbitals as well. You know that the shape of d orbital or the energy of the d shell or d orbital is slightly different from that of S and P. We have done it in the topic on atomic structure. So these 4 hybrid orbitals now need to be oriented so that they are maximum distance apart, and there we go, 1, 2, 3 and 4. It's not a tetrahedral geometry. They are in one plane but directed towards the 4 corners of a square. So 4 corners of a square means it's forming a square and they are in one plane. So square planar geometry is what explains the structure of NiCN4. So we have nickel in the middle and we have Cn, Cn, Cn and Cn. Square planar geometry. And this is confirmed by experimental measurements. This also justifies why this compound is diamagnetic. Again, we see valence bond theory is able to explain, okay? It is trying to justify the experimentally observed values. Now here, I am going to introduce something new over here. We are involving the d orbital of the penultimate shell, right? What is penultimate shell? You have this atom, right? Simplified version. So let's suppose its valence shell is the fourth one. 1, 2, 3, 4. This is the valence shell. One inner to the valence shell is what we call as the penultimate. We are involving the d electrons from the penultimate shell. So that means we are involving something which is coming from the inner orbital. So this type of a complex is called as the inner orbital complex, or because we are taking the d orbitals from a lower level, so low spin complex. Because all the electrons are paired up over here, it is also called as spin paired complex, right? So we have introduced some new terms over here because we are going now to example number 4, right? Have you drawn this? Have you written it down? Very good. Let me take a break for water and we do example number 4. Now here I am going to confuse you. Don't get scared. I am talking about a compound of, or a complex ion of copper over here. CuNH3 whole 4 2 positive. Please name it. And don't forget the double M in the amine, right? Because if you write single M, that's like how you have in the organic compounds, the NH2 group. So don't forget the double M when you name this complex ion. Copper atomic number 29, electronic configuration argon 3d10 4s1. Why 3d10 4s1? Yes, fully filled orbitals are extra stable. Now coming to the oxidation state. Now here the oxidation state being shown by copper is 2 positive. So where does the 2 positive come from? 4s has to do away with 1 electron and we need 1 more electron. Okay, let us take it away from 3d. Now we have 1 unpaired electron. Okay, so we are playing safe because according to experimental results, our compound should be paramagnetic. Perfect, it is paramagnetic. Let's do geometry now. Now I need, because there are 4 ligands, I need 4 orbitals in order to participate in hybridization. So let us do 1, 2, 3 and 4. sp3 hybrid orbitals. How many of them? 4. What type of geometry? Tetrahedral, right? We did it a little while ago. sp3 hybridization, tetrahedral geometry. Oh no! Tetrahedral, square planar. Does it match? No way. So are we on the right track? No. Something is wrong we need to do. So this is ruled out. Let's explore option number 2. Because we are talking about square planar, we said that square planar means it's the, we need to involve, it's some kind of dsp2 hybridization, right? dsp2 means I need a vacant orbital in the d sublevel. What do I do about this electron? He has to accommodate, right? There is some guest coming at home. Okay, come on, pack your bags and baggage and move on to the higher energy level, go on to 4p. That's what the command is. So now I have dsp2. Oh wow, this easily fits into the scheme of things. And dsp2 hybridization means 2, 3, 4. 4 dsp2 hybrid orbitals means, yes, square planar geometry. Unpaired electrons means paramagnetic behavior. What more do we want? There's a problem here. If we are saying that this unpaired electron is in 4p, that means it's lying a little towards the outer part of the house. It's bound to be attacked by mosquitoes. It is bound to be taken away by some other groups. Let's suppose if sulfate comes in and, oh, so not sulfate. Sulfate is already negatively charged. So if you have another positive ion, so let's suppose Cu2 positive, it will say, come to me. You are alone. That means in that case, copper will turn to Cu3 positive. That becomes its more stable state, right? But have you heard about Cu3 positive? No. We know that Cu2 positive is very stable. This ion is also very stable in the complexes. You've done it in your chemistry laboratories as well. So how do we, adjust this? So we need to find a solution to this. Can you think of a solution which should justify the paramagnetic as well as the square planar geometry? Think. Did you spend time thinking? Okay. Now it's a very weird explanation, but it was given by Higgins in order to explain the behavior Higgins, in order to explain and in order to go along with the observed experimental behavior. So let's go on to the explanation provided by Higgins. He said it is paramagnetic. Okay, agreed. Let the unpaired electron remain. Don't touch it. But you want square planar, so that means you want to involve a d orbital. Then why are you bothering 3D? Why don't you look up? Why don't you go a little bit ahead? And why don't you ask the orbitals of 4D to participate? Right? So, but because it's square planar, if we are taking S and all 3p and d, then it becomes sp3d, and that would be how many? sp3d means how many orbitals will be there? 3 and 1 4 and 1 5. We need only 4 ligands over here. He said that it is 1 of s, so it is 4s, and there are 2 of 4p and only 1 orbital from 4d, which will come together to form sp2d hybridization. Yeah, I know. I don't like the look on your face. This teacher is teaching anything that is coming to her mind, anything to justify. I can't help it. That's what is chemistry. This is the explanation. As we said, valence bond theory is trying to justify the observed experimental behavior. And sp2d hybridization means, is it the same as a dsp2? No, it is not the same. Because there we import the d orbitals from 3d, the penultimate. Here we are involving the d orbitals from the outer energy level, the valence shell. So this is called as an outer orbital complex. What is the other name that you can give? Because it has an unpaired electron, it is spin-free complex, right? And because we are involving something for hybridization which is from the higher energy level, we can also call it as a high spin complex, right? And sp2 dehybridization justifies the square planar geometry of this ion, right? Don't be upset with me. I didn't give this theory, right? These are explanations which have been given, and I thought that I should discuss it so as to make you understand that these are explanations in order to justify. Moreover, it's not that there is these hybrid orbitals that is something you can see. These are simply redistribution of energy which is happening in order to accommodate the ligands, right? We go on to example 5. Promise you, this is going to be easy. Example 5 is going to be lovely, short and sweet. We'll finish it. Don't worry. Before I go on to take the next 2 examples, please make a note of the questions based on this lesson. First, why did we need the valence bond theory when we had the Werner's theory in place? So basically, what were the points which were not covered by the Werner's theory that we had to explain it with the help of PBT? In what ways was the valence bond theory successful? What all points could be explained using the valence bond theory? And the shortcomings. Why do we have to keep reinventing ourselves? That's what will be the question for the day. So let's now go on to the next set of 2 examples to make the concept complete. I'm now taking up example 5 and example 6, and if you notice, both of these are coordination complexes involving cobalt. Okay, now is the test for you. Don't worry, you will get the answers, but as I always say, I cannot teach without your cooperation and without your help. I told you in lesson 1 itself. So in this particular compound, you tell me the oxidation number, coordination number, geometry. The only piece of information I am providing you is that this compound is diamagnetic, whereas COF63 negative is paramagnetic. Cobalt atomic number 27 is again what I am providing you over here to help with those who do not know the electronic configuration or to make it easier. It's argon 4s2 3d7, right? So go on to write the oxidation number, coordination number, geometry you just can't predict by looking at it, but probably you will, or maybe the hybridization also you can try. Please pause the video, give it a try yourself. If you've got it wrong, don't worry at all. Nobody gets it right in the first instance. I have barely managed to understand this theory now when I have to teach you, so it's okay, relax. You know why? Because otherwise it's always confusing. Do we have to remember that this is diamagnetic? Do we have to memorize? No, nothing like that. This is experimental piece of information. How do we expect you to know it? Okay? So the question would be probably centered around saying that this particular compound is diamagnetic. Can you explain? So in that case, you will go on to draw the electronic configuration. If you are asked to explain the geometry, then you go a step ahead, explain the type of hybridization. And now that you have enough knowledge of hybridization, you will be able to predict the geometry as well. So give it a try. Okay. So the oxidation number over here is 3. Sorry. Oxidation number over here is 3 because ammonia is 0. Coordination number is 6. Diamagnetic. Diamagnetic means does it have unpaired electrons or paired electrons? Very good. It has electrons which are paired up. This is an important piece of information for us. So, let's start with the example 5. Argon 4s2 3d7. First, allot the electrons according to Hund's rule. 1, 2, 3, 4, 5, 6 and 7. Unpaired electrons are here, right? Oh, we are not yet done. We have 4s2 as well. Now see, the oxidation number equals 3. Don't forget this. Oxidation number 3 means it loses how many electrons? 3 electrons. 1, 2 and 3. Does it still have unpaired electrons? Yes, it still has unpaired electrons. But it is showing diamagnetic behavior. If it has unpaired electrons, it should be paramagnetic. So what can you predict about its hybridization? Very good. The electron pairs up. So we have 1, 2, how many ligands do we need to attach? 6. So I need to take 1, 2, 3, 4, 5, 6. What is the name of this hybridization? Very good. D2sp3 hybridization. Correct? How many hybrid orbitals? 2 of D, 1 of S, 3 of P. 2 plus 1, 3, 3 plus 3, 6. So I have 6 hybrid orbitals. Now these 6 hybrid orbitals have to be oriented so that they are maximum distance apart from each other. We have done this geometry earlier as well. So it will be 4 in one plane, 1 above it and 1 below it. So let's do it then. We have this would be the geometry of this complex. It's not exactly the same, but this is the easiest way to represent it. I'm not asking you to make an octahedron with paper and all. This is the easiest way to understand. So 1, 2, 3, 4 in one plane, 5 and 6. All of them at a bond angle of 90 degrees. Now if you notice over here, we are involving the d orbital of the inner shell. Hence, what is the name? Yes. What type of complex is it? It's an inner orbital complex. Spin free or spin paired? Very good. It is spin paired. Right? And inner orbital, spin paired, and what is the third term that we have? Yes, it is low spin complex. We are involving d orbital from the penultimate shell. Correct? So what will be the geometry over here? What will be your answer? Octahedral, bond angle 90 degrees. Example 6. Did you try it yourself? Were you able to do it? Okay, I like that smile. Oxidation number again 3. Coordination number 6. But it is paramagnetic, right? So how do you explain this paramagnetic behavior? Means it should be having unpaired electrons. Correct? Geometry we have to see next. Now cobalt 3 positive. 1, 2, 3, 4, 5, 6 and 7. Right? Because cobalt loses 3 electrons in order to come to oxidation number 3. Unpaired electrons. Perfect. Unpaired electrons are here. We are playing safe. Now, we have to accommodate 6 ligands. How many orbitals do we have at our disposal? 1, 2, 3, 4. Oh, we need to make space for 2 more. How do we do that? Very good. We involve the 4d orbitals as well. And how many of 4d should be involved? Very good. Because we need 2 more. So we have 1 and 3, 4 and 2. What type of hybridization is this? Very good. It is sp3d2 hybridization. Is it the same as D2sp3? No. What will you call it as? What type of complex is it? It's an outer orbital complex, right? It's a spin-free complex. It's a high spin complex, right? And what will be the geometry of this complex? Very good. Again, octahedral. Right? So if you notice over here, we've got the same central atom, we've got different ligands. But the same metal atom is behaving differently under 2 different situations. One it is dia, the other it is para. Hybridization is different. And this is the major drawback of valence bond theory. It is not able to tell us whether that particular, it is not able to predict. It is not able to predict the geometry. It is not able to predict the magnetic behavior, right? Then there is no talk about color as well, right? So if we are talking about the drawbacks of valence bond theory, it's not making any mention. Now, color is something which you are using in the laboratory as well, right? You are testing the ferrous ions, the ferric ions by the color they give with potassium ferrocyanide and potassium ferricyanide, correct? You talk about these colors. So we know that color is something which is associated with coordination compounds. There is no mention of that in the valence bond theory. Then when we talk about magnetic behavior, one compound or one complex ion is having 3 unpaired electrons, the other may be having 2. There's no mention of the quantitative measurement of that magnetic behavior of that complex ion. Yes, it is able to help us in defining the geometry. It has been successful in telling us as to why some elements are able to form complex compounds, the others are not. But there are drawbacks as well. And that is where the crystal field theory comes into the picture, right? So you know what I'm talking about. Lesson number 6 is what we will be covering next. CFT, the crystal field theory. Before we go on to that, I would request you to attempt a few questions in order to probably examination questions, so that you are able to get a hang of this particular concept of valence bond theory. You are able to understand it clearly. If you have been able to relate to this channel, an earnest request is to share it with friends and classmates so that we can spread the joy of learning more and more. Happy studying to all of you. See you in lesson 6.